Hello again. So in the last video, we had left off on problem number 4, taking antiderivatives, and we're going to pick it right back up, starting with number 5, also an antiderivative problem, except this time we have a little bit of physics. So we have v of t. Well, antiderivative, we know that's position. So then we just antidifferentiate this function to get 1/3 t to the third minus 2t to the 3 over 2 plus our constant of integration. Since we are going backwards, we have to add that constant. Next, we go ahead and just apply our initial value. So we do s of 4, which is 8, equals, and this is going to be 64 over 3 minus 2 times 8 plus c. Solve for c. c will give you 8 over 3. Then, for the last step, all you have to do is combine everything that you had and put it all together. So we have the s of t is going to equal 1/3 t to the third minus 2t to the 3/2 plus 8 over 3. And that will be the final answer for part A. Alrighty, then moving on to part B, we have the same exact type of problem. The only difference is that we're starting with our acceleration instead. So we're going to differentiate twice. So antiderivative of acceleration is velocity. So we have antidifferentiating this, we have 1/3 t to the third minus 2t squared plus 6t plus c. Next, we want to anti-differentiate one more time, so we get position. So the position of t equals 1/12 t to the fourth minus 2/3 t to the third plus 3t squared plus ct plus d. Then, after that, we can apply our initial values that we have. So if you do s of 0, 9, you end up getting 9 equals d. And for the second one, we did 20 equals 1/12 minus 2/3 plus 3, and then plus c plus d. And d is actually 9, so just go and substitute it in. Solve for this, you'll get c equals 103 over 12. For the final step, again, we found our constants, both the constants of integration. We just plug that back into our position function. When we do that, we will get s of t equals 1/12 t to the fourth minus 2/3 t to the third plus 3t squared plus 103 over 12 t plus 9. That's 12. All right. And that is all for that problem. Oops. There we go. Moving right along, we go on to number 6. This is your classic sketching the graph. There'll probably be one of these on your test tomorrow. Wouldn't be surprising. Just know how to do these. We'll start off by part C tells us that there's an asymptote. So at 0, there's an asymptote. Right as it goes to infinity, it's going to approach 0. So just go and draw it in nice and simple. Ready? We also have an odd function. We know that, so we know it's odd as well. But we'll go ahead and do that. Probably our last step. That'll probably be the last step. Anyhow, we'll go ahead and do this next portion. Okay, so I'll show you a little bit of work instead of just kind of giving you an answer and telling you to compare it, just so you can see a little bit of thinking behind it. So we'll go ahead and start with our, what I like to do, I like to draw kind of like 2 lines. So the first line will have the first derivative, the second line will have the second derivative. But with that being said, so 0, 1, 2, from 0 to 2, it will be increasing, and then from 2 to infinity, it will be decreasing. So positive slope, negative slope. Got that down. Next part I kind of like to do, I will draw another number line. This one will have the second derivative then. So this one has 0, 1, 2, 3, 4. So 0, 4. And between 0 and 4, it is going to be decreasing, or not decreasing, my bad. It'll be concave down, and from 4 to infinity, it will be concave up. Yes. So next we have everything that we need to do to be able to draw this graph. So let's go ahead and do that. Beginning at this 0, so I'm just going to go ahead, I can start at 0, 0, why not? And then we have 1, 2, 3, 4, just to give us some points. 1, 2, 3, and 4. Okay, as we can see, so we want this to go from increasing to decreasing, right? Or increasing to decreasing. So we're going to have like some sort of maximum. So, and it's all going to be concave down. From 0 to 2, we're going to increase in concave down. Then we're going to put a point there because that is going to be a maximum. And it's going to be and then it's going to go from increasing to decreasing, and it's going to keep decreasing. Then at 4, it's going to switch concavity from concave down to concave. Whoa, that is weird. Let me fix that for 2, concave down. All the way like that. Good. Next, we want to go ahead and just apply then the next part. So that is just putting the 1, 2, 3, 4. That's good. 1, 2, 3, 4. The odd part of the function, right? So I'm going to do a combination of kind of a visualization and also some points, so that kind of gives us some directions. So this is 2, and it's kind of between 3 and 4. So there's about a point there. And then also I have about 4, comma 1. So that goes to -4, comma -1. So those are 2 points. And now I'm just going to go ahead and sketch in this curve to match. That's pretty good. Alrighty. And, well, I glitched a little bit. Now that's going to be an asymptote. And let me redraw that in. I think it made my screen glitch and it kind of missed it. So, like so. Yeah, it's close enough. Close enough. So we have some points, and you can tell that it's definitely, you know, not a function, kind of reflected over that same axis. But good. As long as you have something like that, it'd be pretty good. Keep moving along. Now this is the one we really use guidelines to sketch a curve. So we start with our, oops, not bad. This is what I want. Good. We're going to start with some sort of graph, right? So go ahead and put that there. Starting, we know that there's an asymptote at 1. And I know that because, drag a little farther out actually. We know there's an asymptote because of the bottom. So we know that there's an asymptote at x equals 1. And then we know that there's a point 0, comma 0. Now, that's all we really can get from just looking at our original function. This is where derivatives really come in handy. They tell us increasing, decreasing, also concavity. So we can get a pretty good idea what this graph looks like. So let's go ahead and do that. So to go into our f prime of, oops, let me go ahead and switch colors back. So our f prime of x, and this is just using our quotient rule. And since you guys are probably pretty comfortable with derivatives by now, I'm not going to show all the work for it, but you should get for the first derivative that 2x to the third minus 3x squared all over x minus 1. Oh, changed to a trapezoid. Interesting. X minus 1 squared. So when you plot your critical values, and when you plot your critical values, technically you don't need to include 1 because that's not included in your domain, but I just usually put it there just in case. So I will go ahead and actually I'm going to replace where I drew my line. There we go. But we'll draw the line right underneath the graph so it lines up. So from 0, and you'll get 0 and also 3 halves. So because when you factor that out, you get x squared times 2x minus 3. So we have critical values at 0 and also 3 halves, which is 3 halves is like, that's 2, 3 halves is about here. So this is 3 over 2. 0, 1, 2, 3 over 2. Yeah, good. Okay, so we have those two values, and so what you'll end up getting when you test your regions, you'll get that's all 0, negative, negative, and this will be positive. So yeah, all this and other things are right will be positive. So that tells us kind of the general shape of, or the slopes over certain intervals, increasing, decreasing. Next, we need to do the double derivative, right, or the second derivative, to give us concavity, and this will give us a really good idea by what it's going to look like. So when you do your chain rule again and do some algebra to make it look pretty, it'll end up being this over, all this will be over x minus 1 squared. So you go ahead and get this. Then when you set this equal to 0, yeah, so we have the x equals 1 on the bottom still, but go ahead and pull out an, if you pull out an x, you'll get 2x squared. Actually, you can pull out a 2x. Pull it at 2x, then you get x squared times x squared minus 3x plus 3. And you'll note that This top is actually everything has no real roots. So this is no real roots. So that means that when you set this equal to 0, you won't get like an x. You won't really like factor or get like x equals something. It won't cross the x-axis. In other words, well, that should be to the third, I believe. Yeah, to the third. I messed up. There we go. So then next thing you want to go ahead and do and plot this one on a number line then. So for this, all we have is 0, and I'm actually going to go ahead and plot the 1. So we have 0 and 1. When we do this, we test regions vary concave up, concave down, and concave up. And that's just by choosing numbers that fill in between those regions. Now we're at the point where we can get a pretty good idea and a pretty good sketch of this thing. So let's go ahead and test it out then. Oopsies, I dropped something. Anyhow, scrolling back up, we know that at 3/2, there's going to be a some sort of, if it goes from decreasing to increasing, it's going to be some sort of minimum, right? So it's going to look something like this. And I know it's pretty high up because if I were to plug in 3/2, it'd give a pretty big number, or a bigger number. It'd be definitely above the axis. Anyhow, the next part I want to do is I'm gonna look at, so everything then to the left of this 3/2 is going to be concave down, right? Concave down. So actually, I think I messed up there. That feels like positive. So go ahead, and we know it's concave down, but it's going to have a point of inflection at 0, so it's going to go from concave up to concave down, so we know that it's going to look something like this. Go ahead and draw this in. Both will be approaching those axes. And this is a pretty good idea. You can go ahead and graph that on a calculator and see, but this gives you a pretty good idea of what it looks like, just based on what you got from using derivatives. But that is all for that problem. And I'm going to go ahead and stop the video because I don't think I have enough time for problem 8.